All right, everybody. So back to the resources page. Let's do a couple things. First thing I want to do is let's crack open this data sheet. Today it's going to be a Word document, so just open that up. You'll recognize it from class. Oops, let me pull it over here so you can see it. It's just got some fairly straightforward data sets we can play with. So we'll play with these in class. Or now, excuse me. I've got some fun ones we can talk about once we're in class together. I've also got a few I want to collect in class, but I want to look at two. Let's see, we'll do two of these data sets today. Let's see, IQ or speed. Let's do the speed one. So we're going to focus. We'll skip the IQ one. It's kind of boring. So we've got data collected along a road, and just so you know, it's a road in Bend. It's data that I've collected in the past. The speeds along Archie Briggs. So we're going to look at these two data sets. Now, to keep the lifting light for us, I want you to also open up your Excel calculator. So let's go back out to here, and we'll do this. Open her up. It's Excel. It might take a little while to load. Let's see how quickly it loads here. Did it already load? There she is. She's good to go. Okay. So, you know, in class, we've been playing with the single proportion hypothesis test sheet, which is great. I want to talk about the data that we've got over here, though. Okay, let's take a look at this, and I'll blow it up so we can see it better. Okay, these are speeds of cars tracked on a road. So it's speeds in miles per hour. Now, I'm going to estimate with you all how these cars are behaving with respect to a 30-mile-an-hour speed limit. So you think about all that, though. These are speeds of cars, speeds, miles per hour. You're talking about 2 units, miles an hour, both of which are continuous. So these are measurements, not things that are counted. And because they're measurements, we need to take a look at whether or not these things are discrete or continuous. Measurements have to be continuous. Now, sometimes we want to find averages of discrete things, but very, very rarely. We'll talk about that in class on Tuesday when we reconvene. Generally speaking, when you have continuous data, weights, lengths, times, temperatures, things like that, you measure them and then you find averages of them. So that's what we're going to do here. We're going to try to figure out whether or not these folks are speeding, whether there's statistically significant evidence that these folks are speeding. So let's take a look. The first thing I want to do to help this test is I want to look at a template sheet. Now let's go back to your resources page. Sorry, this is a little bit scattered. I'm not used to doing all this on a computer. Usually I'm sitting in class with you all. There is going to be in the back here a template for hypothesis test. Let's crack that open. Okay, so this is a Word document. So now we got 3 things open. We got the data sheet open, we got the template for the hypothesis test open, and we've got the Excel calculator open. So we know we're going to be testing the variable mu. Now the reason we're going to do that is because we're talking about the average speeds of these cars, on Archie Briggs. And what we've just done, actually, friends, think about that. We've just defined the variable 2. We've defined mu to equal the average speed of the car on that stretch of road. Okay? As a matter of fact, this is an experiment I wanted to do with you all in class. I just never was able to pull it together enough this term to get you guys out on College Way and time the cars. But anyway, that's okay. I got my own data from Archie Briggs. So the average speed of a car on that stretch of road. Okay, so let's look back at the data again. I know that the speed limit of these cars is 30 miles an hour. Now let's look at the data. Let's look at my individual data before we go to the police data. We'll give you a story about that too. The individual data, we've got 5 cars going between 15 and 20. We've got 9 cars going between 20 and 25, 11 cars going 25 to 30, and so forth and so on. Looking at this data, if you put a line right there, which is the exact divider between those going under and those going over 30, you got a sizable chunk going over 30. So it might look to be that cars are speeding. And I'll give you the backstory. The reason I care about this is because this is a road I bike up and down every day. Now, generally speaking, I bike up and down it. I bike up it at least when it's not that heavily trafficked. But this data was not collected at the time I bike it. This data was collected in the middle of the day. And these speeds are pretty fast. I mean, 40 miles an hour down Archie Briggs, this car right here was whipping down there pretty quickly. It's a north-facing road. In the winter, it can be very slick. It just scares me a little bit when people are going that fast. So I want to know, are these cars speeding? So what I'm interested in as a researcher is I am interested in checking whether or not these cars' average speeds are greater than 30 miles an hour. That's what I want to know. I'll even put miles per hour there if you want to have a unit. I want to know, is the average speed greater than 30 miles an hour? Okay? Now, the null hypothesis, you might think it should just be equals. Technically speaking, it should be less than or equal. But the idea is, it's the opposite of what my claim is. My claim is going to be it's greater than 30. The null hypothesis is just the opposite. You hope the cars go around the speed limit. Let's see if the data bears that out. Okay, we got some error analysis here. Okay, a type 1 error, as we've kind of talked about quite a bit now, would be believing this when this was actually true. Okay, believing this when this was actually true. So a type 1 error, I'll keep this red font, would be claiming the cars are speeding when they actually aren't. Okay, that would be a type 1 error, false positive, right? A false negative, type 2, would be saying the cars aren't speeding when they actually are. I'm going to let you decide which one of those two you think is worse. I have my opinions, but I do not want my opinions to influence yours. So I'm going to let you decide which ones you think are worse in that scenario. And it's okay, whatever one you say, as long as you back it up with good logic. Let's skip down. I'll skip over 5. And let's look at 6. Now, this is where it gets interesting, because this is where it changes a little bit from proportion studies to mean studies. For proportions, we liked using the Z distribution. For average studies, we're going to switch over to the T, just like we did for confidence intervals. But that's about the only difference, except for the mathematics of the test statistic, which I'll get into in class with you next week when we regroup. Because honestly, I'd rather just, this is kind of a bridge, like I said, between where we were and where we're going. We'll get into the nitty-gritty math, so I want to answer all your awesome questions together. This is really just to tide you over until we get to that time when we're together. So for a T test, we have to, let's go to the Excel spreadsheet now, because this is the same point we would go to our Excel spreadsheet for a single single proportion hypothesis test. We want to go to a single mean hypothesis test. Now, if you take a look up here where we put our data in, notice we need an X bar, a sample average, we need a sample standard deviation, and we need a sample size. Okay, now we know at least one of those three things already, kind of, but we actually don't know, we haven't calculated any of them. All we know is this is our data. This is our data right here. What we need to do is take this data and turn it into a sample average, a sample standard deviation, and a sample size. And this is why we're going to have to go back to old sheets in our calculator. If you back up to the Math 243 sheets, we've got ourselves some grouped data. Let's blow this up so it's easier to see. We've got ourselves some grouped data right here. Okay? This is the kind of sheet we're going to use to transform our group data into some statistics we can actually use. So looking back at our data, 15 to 20, 20 to 25, just like we did back in the day and we do every once in a blue moon, whoops, we are going to transform that data by looking at the midpoints of 17.5, 22.5, 27.5, and so forth. Let's see if Excel is smart enough to recognize that pattern and pull it down. It is. I think, was it 47.5? I think is the highest we have to go. Oops, wrong sheet. Got a lot of stuff open right now. Yeah, 47.5 because it's 45 to 50. And then all we got to do, let's see if I can do this. Can I copy these? That would be phenomenal, wouldn't it? Looks like I can. There we go. We can delete all these, and then we're left with our data right here. That's our data. That's our data. So we've got everything transformed into the midpoints here, the frequencies here. And if you look over here, you can take a look and see that, yes, the average is indeed 31.66 with a plus or minus of 6.19. And there are 83 cars in the sample. Just like we did back in the day, I'm going to copy these over to the single mean hypothesis test area. Paste it in just like we did back in the day. Okay, so now we've got 31.6 miles an hour. We got a plus or minus of 6 miles an hour. We've got 83 cars in the sample. The only thing we got to do is adjust our null hypothesis. We're not comparing it to 3 miles an hour. We're comparing it to 30 miles an hour. Okay, so that's going to be the one we're going to be looking at. All right, so we're set up good to go here. All we've got to do now is we have to crunch our numbers down here by picking the correct tails. We're going to leave 95% confidence just for the sake of argument. I believe the tails we want are, or the tail we want is right, because we are looking to see if they are exceeding the speed limits. We're going to pick right tail and then scroll down. And we get two very important numbers here. First of all is the test statistic. I get a test statistic of 2.4. Comparing this to our z-tests, it means the same thing, 2.4 standard deviations away. It carries a p-value of 0.85%. Now read that correctly. That's not 85%. That's 0.85%. So this is not 85 out of 100, it's 85 out of 10,000, which is less than 1%, which is definitely less than 5% if we're using that as our guideline. So heading back over to this template, the test statistic is T, let's copy it from here. T is about equal to 2.4, and that's standard deviations away. The p-value, if you want, and you have a couple choices here, of course. You can write p equals 0.85%. I'll make that red so it matches. What do you say, huh? Make it a little bit bigger so you can see it. P is about 0.85%. You can put P as less than 5%. I mean, you can pretty much do, as long as you're representing it accurately. But however you look at it, it's small. It's a small p-value. A small p-value, going back to everything we've been talking about since, I don't know, 3 or 4 weeks ago, a small p-value makes it easier to believe the research hypothesis, which means we should reject the null because the research is looking pretty good, which means that it appears that the cars are speeding. Now, this is statistical. Appears. It appears that the cars are speeding in a statistically significant way. Someone else might look at the data and say, yeah, but the average speed is only 31.7. That's not worth worrying about because it's only 1.7 miles per hour above the average speed. But again, remember, this is not practical significance. This is statistical significance. Statistical significance. So there's one example right there. How's that make sense? Hopefully it does. If it doesn't, we're going to do the same one replicated again, but we'll do it with the police's data. So hang tight, we'll do that one on the next video.